So you got a remind message this morning. It seems that a lot of students are getting the thing and they're being quarantined. So for the foreseeable future, whenever I go over something that I think everyone should see, I'm going to make a video of it and put it on that Canvas module for that day. I know I've said I would do that in the last few days, but I hadn't worked out my system, and so I'm starting now. Okay, they're not going to be obviously up until later in the day though, because I won't have time to do the uploading until after school. But they will be there if you're going to be at home. All right, so that'll be the last thing, Mr. Graham's video of whatever we do today. What we're going to do today, we need to catch up a little bit. I'm a little behind Mr. Louise, a lot behind, like several days, a few days. It's because there's astronomy in this unit. When you get me talking about astronomy, I just ramble. And then you guys have questions, some of them good. And, just kidding. And then if we just talk, yeah. So we got to get back on track. And so I felt the best way to streamline that is just to do a set of fill-in-the-blank notes. That will kind of tie everything together into one nice little reference sheet that you can use when we do the problem set. Now raise your hand if you've started on the quest assignment. Okay, so we got a few. Go ahead and stop that. We're not going to do the quest assignment. And if you did problems on it, I will figure out some way of giving you credit for that. Whether it be like credit on a, I don't want to say a test question, but another daily grade. If you lose any points, then I'll add those to that daily grade. Okay. I'm making a list of those students. So actually, I'll just go through quest and see who started it. But otherwise, don't. We're going to do this worksheet. The quest would have taken too long. It's too long of an assignment, and I need to get us back on track. I don't want to give you guys too much to do. So we're going to do this worksheet. We're going to work on it together towards the end of the class today, and then a little bit tomorrow as well. Okay? And then you'll take a picture of this and submit it on today's module, but you submit it tomorrow night. I think the date says tonight, but I need to change that to tomorrow night. Okay, so let's go through the fill-in-the-blank notes real quick. And I'm going to go through it briefly because we already know all this stuff theoretically. I will point out, if any of you are not here today, that if you don't want to watch my video because I'm too boring or I ramble too much about things not relevant, then you can watch Mr. Luis's video. He's much more focused. So yeah, he goes over the same set of notes. This is his video from last year. But I'm going to go over the same thing just in case there's questions I want to address and stuff like that. So the notes, let's just go ahead and fill them in together. Go through them. This unit is all about circular motion, centripetal forces, centripetal accelerations. We got our equations. I do like having the sigma symbol. Right. And I do like putting the little subscript on the A for centripetal acceleration. And remember, it's because v squared over r is the acceleration. That's what makes this. This is essentially Newton's second law. All right. When something moves in a circle, we're filling in the blanks. It can be going, this is kind of obvious, fast or slow. Whether it's fast or slow very often is important though. If you take a turn in your car and you go take it very slow, are you in danger? Not really. If you take that turn at 75 miles an hour when the speed limit's like 15, are you in danger? Yeah. So you got bigger speed, it's different circular motion. To measure that speed, we would need the distance traveled around the circle and the time it takes to make that lap. Remember, the first physics equation you guys ever learned was speed is distance over time. That is an equation that describes motion. That is related to the kinematic equations. And you've known that, if you're like most students, since at least middle school, maybe even elementary school. So that's what we got to do here, right? So the distance covered, which we have to convert to meters if it's not. If you didn't convert your centimeters to meters when we did the lab, your answers not only would be not very accurate, but they would have been horribly inaccurate. And that would be the circumference, which we know is 2 pi times the radius of the circular motion, of the circle through which the object is moving. You don't have to remember that, but hopefully you do. I think it's on your formula sheet. If not, I'd put it on the board. I don't care. The time then in seconds, that's what the other thing we need, right? We need distance and time. The time we use is the time required for an object to complete one rotation or one complete rotational cycle, sometimes it's called. That's called the period, and the symbol for it in our equations is a capital T. It is a time, but it's a special time, so it's not little t, it's big T. All right, and if you ever need me to slow down, just let me know, but I do need to erase this so I can scroll up. Need me to repeat, though, please let me know. Now that we've established distance and time during circular motion, we can calculate for the speed of this object. And again, speed is distance over time. The variable we use is v. It is speed. We say speed because it's not velocity, because the velocity is not constant. Right? If you want to be real nitpicky, if you're like a real nitpicky physiker, you could say, well, that's velocity because it's got the vector symbol over it. We leave the vector symbols off a lot because it just clutters the algebra. But if I wanted like full-on correct symbols, it's v with a vector symbol. That is velocity. And if I write it without the vector symbol, then it's like, well, that's speed because I don't care about the direction at that point. Do you need to really pay attention? Not really, but just know. Right? Speed. In this case, in this context, is speed. And it's distance, but we know that distance is 2 pi times the radius. And we know the time is the period, capital T. And so we have this rather easy problem. What is the linear speed of a race car? You know race car spelled backwards as race car? They have numbers like that too. There's a class of numbers that palindromes, is that what it's called? I think they're called palindrome numbers. And there's weird relationships between palindrome numbers and prime numbers or something. I remember watching some weird thing. And there's one that's got 666 right in the middle, and so it's like called the evil palindrome number or something like that. That's kind of funny. So what is the linear speed of a race car completing a circular lap with radius of 100 meters? Radius 100 meters. Kind of doing guess method kind of thing, right? In a time of 23 seconds. Says, what's the linear speed? Notice it does say linear. That kind of throws students off because you think linear and you think straight line. But when you talk about like linear equations don't need to be lines. You'll learn a lot more about this if you major in engineering or anything like that, STEM fields, and you have to do linear algebra in college. When we say linear, we just mean the straight line motion. Even if we're curved, we're just talking about if you take a radar gun and put it on that object, what speed does it tell you? That's what we're talking about when we're talking linear speed. The reason that we make that distinction is because the other type of speed that we deal with in physics mainly is rotational speed, right? And so that's not related to linear speed at all. Even if I'm curving, I'm talking how fast am I moving meters per second. And that's to distinguish that type of motion from rotational speed, which we don't measure in meters per second. We measure in what, do you think? Degrees per second. Or radians per second. Oh, radians are more better than degrees. Degrees we use more, but radians are more fundamentally neat. Okay, so we're looking for speed v. Small aside there. Do we have an equation for that? Yeah, it's this one. Why am I not using Newton's laws to analyze centripetal forces and stuff? The problem doesn't mention forces. That's when we use Newton's laws, when we have to analyze what the forces are doing to the object. Here, we're given two things and ask for a third that we don't need to even worry about that. No free body diagram necessary because we're not worried about the forces here. Because what we need, I can calculate with the given information without worrying about that. So I just use that equation. V equals 2 pi r over the period. And I write the equation every single time first because it's a good habit. Equals 2 pi times the radius, which is 100 meters, divided by the period, which was 23 seconds. And you can do that in your head, right, Peyton? What'd you get? 4. 4? 27.3? Yeah. 27.3. Notice the units. Dimensional analysis, if I was doing it, the radius is measured in meters, the period is measured in seconds, so the units are meters per second. Alright, it's pretty fast. It's like from the 0 to the 30-yard line in 1 second. People don't run that fast, right?
Not even close.
Okay. I don't know the fastest human speed in meters per second.
I think it was 19 miles per hour by Usain Bolt.
I can't do that in my head. Okay, good? Any questions? Let's keep going. Let's keep trucking. All right. When introducing this unit, we said that objects traveling in a circle have an acceleration. Acceleration. And remember, that's the stumbling block a lot of students have, is that, well, it's not changing its speed, so how could it be accelerating? But it's accelerating, even if it is traveling at a constant speed. There's several ways of knowing that that has to be the case. You can't move in a circle without a non-zero net force. If the net force is 0, it's going to move in a straight line. So to get it to not move in a straight line requires a force, and that force can't be offset by another force. Therefore, Newton's second law must apply.
It was 12 meters per second.
12 meters per second?
Yeah, so not even close to that.
Okay. So fastest humans are about 12 meters per second. That's still fast. That. What's that?
It was 27.33 miles an hour, which Usain Bolt's top speed.
Wait, now I'm confused.
Wait, what? That's, well, I guess maybe the math works out, but like, it's 27.3 meters per second on the answer. You know?
Oh, I was saying Usain Bolt's top speed was 27 miles an hour.
Okay. Oh, Usain Bolt. I was like, what did he say? Okay. I mean, I could beat him, but I just choose not to compete.
Okay.
All right, so even if it's traveling at constant speed, a couple reasons that we know that happens. Obviously, there needs to be a net force in order to get an object to move in a circle. Therefore, Newton's second law must apply. So if there's a net force, there has to be an acceleration, even if it's moving at the same speed. Also, whenever I don't want to get too much into that, but yeah, that's one way of knowing it. How do we calculate that centripetal acceleration? Well, it's the linear speed squared divided by the radius. Or centripetal acceleration equals linear speed squared divided by the radius. Again, how do we know that? Take Physics C next year. Kristen, find out. Are you a senior?
Yes.
You're a senior.
I like the 8th time now.
By the 10th time, I'll have it. Remember that if we have an object experiencing acceleration, we must have some net force acting on it, which means we can use Newton's second law, which is right here, but I'll write it again right here. Sigma F equals mass times acceleration. And if the net force is centripetal, which for us it will be, we put the little c subscripts there, and we're good to go. Because our object is moving in a circle, we'll call it a centripetal force. This is a center-seeking force. So we could say if we only have one force and it is centripetal, well, really in this column, just put the same thing. Same thing. That's the net force. Centripetal force equals mass times centripetal acceleration. But then if I substitute v squared over r in for the centripetal acceleration, I can combine those into a single equation. Let me erase this so I can scroll up and do that. Rewriting the centripetal acceleration with its own equation, I have the net centripetal force equals the mass, and instead of centripetal acceleration, I can substitute v squared over r. These are things we already know. We're just summarizing it into a nice single sheet where you have reference to it, so we can start doing some problems. And I write it this way because obviously this is what it looks like when I directly substitute v squared over r in for the centripetal acceleration. But when I'm doing my math here, I don't like it written like this. It makes it harder to like multiply and divide other stuff, at least conceptually. And so I would rewrite that as the net force net centripetal force is mv squared over r. And if you don't see why that's true, m I can make a fraction by putting it over the invisible 1. And when you multiply a fraction by a fraction, what do? Multiply the tops, multiply the bottoms. Okay? So m times v squared is mv squared. 1 times r is r. And now solving this, rearranging it for different variables is easier in my brain here than it is here. So if you are similar, then you might want to do the same. Okay. Now this is kind of weird here. The wording I think needs to probably be changed a little bit, but so sometimes we do, and we're going to see an example today, when we have more than one force contributing to a centripetal force. And so you can have multiple forces contributing to the centripetal force, or only one, obviously. And for us, for the problems that you're going to have to do on the test, and for the majority of them on the assignment, you're only going to be dealing with one centripetal force. We are going to do an example today that I like doing even if you don't have to do it on the test, because it explains some things that you already have experienced in your life, especially if you've ridden some roller coasters and you like roller coasters. We are going to briefly talk about a vertical circular motion. Okay. When drawing free body diagrams and determining whether we have a positive or negative value for forces, we'll determine that by whether the force points into the circle or out of the circle. Just fill this in for now and take my word for it. If you're saying to yourself centrifugal forces point away, don't worry about that. Just fill this in, and then when we do the example problem, I'll tell you why. But if you do have forces that point away from the circle, if the force points into the circle, so that's what we're already used to, then we'll say it'll be a positive force. If it points out of the circle, and it can do that without being a centrifugal force, and I'll show you how in a minute, then it will be a negative one whenever we apply Newton's second law. Okay. Again, don't worry about that too much. Now, you do not, by the way, have to be traveling in a perfect circle in order to experience the effects of circular-ish motion, I would say. The reason we do circular motion first is because it's the easiest case of curved motion. If you want to do elliptic, like circular motion, say you're in a circular orbit like the Earth around the sun. Constant radius, constant speed, roughly. And so we have a nice stable orbit. It's easy to describe that, though, because the speed that he's moving at doesn't change, and the radius of the circle doesn't change. But then you talk about like long period comets, long period orbit comets, ones that have periods in the hundreds, sometimes thousands, sometimes tens of thousands of years for one comet year to go around the sun one time. Their orbits are like this. Right. So why do we start here? Because everything's nice and neat. Constant radius, constant speed, it's easy to absorb the physics that way. Here, the comet is barely moving. If it's a long period, 10,000, 20,000 year period comet, when it's the farthest away, it's moving so sluggishly, it is just chilling, it's just moving along. But when it's close to the sun, by the way, that's when we get the comet tail, and it always points away from the sun because of the sun's radiation. When it's there, it's moving fast. It's moving super fast. And so everything changes here, right? The distance between the two objects changes, and the speed of the object changes. To describe that with physics, you have to be able to do this first. So this is why we start with circular motion. Okay? And then you can break ellipses into any type of curved path. The mathematics is similar, but it gets more complicated because circles, the equations for circles are much easier than the equations for ellipses and hyperbolas and all those other curved shapes. Okay? So anyway, bottom line, you don't have to be traveling in a perfect circle in order to feel these effects. Centrifugal forces these are perceived forces that are not real or aren't real. They arise from the fact that an object will want to keep moving in a straight line which is part of Newton's first law, the law of inertia. For example, if you're banking your turn in a car at a decent speed, you may have noticed that you get the feeling that you're being forced out of the car. That's because your body wants to continue moving in a straight line path, but and your body's inertia is resisting a change in your motion. Camera's right there. So say I'm in my car and I'm driving away from you guys, okay? And I turn hard to the left. I feel like I'm being thrown this way. That's not the case. I turn to the left, the car starts turning to the left. My body wants to keep going in a straight line because it has inertia, a resistance to a change in motion. And so my body, the top half of my body, if I'm not putting my arm on the armrest, the top half of my body is just kind of freely floating. So the top half of my body keeps going straight, but the bottom half of my body where I'm sitting on the seat and it can provide the centripetal force on the bottom half of my body, the bottom half goes with the car. The top half keeps going straight. In my frame of reference, it feels like I'm moving this way. But that force, it doesn't exist. That force that you feel like in the frame of reference of the car doesn't exist. Why? Because you're in a frame of reference that's accelerating. And so you end up seeing forces that aren't there. Someone watching from the side, though, would just watch you move in a circle with the car, and the top of your body would just kind of lag behind a little bit. Or you're still moving in a circle. Okay. So let's do an example problem. This will be the most complex analysis of circular motion that we'll do in this class. I like doing it even in classes. I would do this with on level because everyone likes roller coasters. Some of you daredevils, Hayden, or skateboarders, maybe just skateboarding through loops. You ever seen skateboarders go through loops? Yeah. Would you ever try that? Would you try it? I would. Would you?
I would.
Okay.
Not could.
You know how they start, right? When they do it for the first time and when they're practicing, they get a bunch of friends off to the side of the loop and they have mattresses and they push the mattresses once they go up, especially the first time because you're not staying through the loop. Like you think you just stand on the skateboard and you go through. Oh no, you got to constantly be changing your body positioning and your center of gravity and you got to feel it, right? Not that I would know that. I know people that can do that and yeah. You ever know anyone that's really good at skateboarding? How many broken bones have they had? A lot. That's why I never got good at skateboarding because you have to be good to know all the tricks and do all the crazy stuff. You gotta break bones to get that good. Anyway, so I am going to go over an example that's more complicated than what you're required. Do I have time? Yeah, I got time. And it's going to be a vertical circle. And as we'll see, the physics of this, like identical to the physics of a roller coaster going through a circular loop. Right, Safe? You ever been on a roller coaster?
Yes.
What's your favorite roller coaster? You're taking too long.
Okay.
All right.
Thank you.
So we're going to do the problem as if we're analyzing the motion of that ball on the end of a string. And so that we'll assume it's 4 kilograms. I think that one is actually more than 4 kilograms. It feels like it. It's attached to one end of a circle, 2 meters long. If the length of the string is 2 meters, what's that telling us? The radius of the circle is going to be 2 meters long as well. If the mass is swung in a vertical circle from the free end of the rope, vertical circle, what is the tension in the rope when the mass is at the blah, blah, blah? We're changing the end of this. Whoever wrote this problem, I think it was Safe, made it very bad. So cross out. We want when the mass is at its lowest point, if it is moving at, cross out a constant, because that's literally not possible in this scenario. It's possible, but it requires silly stuff. Moving at 5 meters per second at the bottom. That's what we want. We want to say, what is the tension in the rope when the mass is at its lowest point if it is moving at 5 meters per second at the bottom of the swing? Okay, the bottom of the motion. Does that make sense? Are we good with that? Okay. So now that we know that, I'm going to go ahead and just write all that stuff over here, actually, so I can take the projector down. So my mass is 4 kilos. The radius of my circle is going to be 2 meters. and my speed, V, and I'm going to put B for bottom. At the bottom is going to be 5 meters per second. Okay? Yeah.
Do we have to convert the mass to grams and stuff?
No.
Oh.
MKS. Tattoo it on your brain. MKS. Meters, kilograms, seconds. It's confusing because none of the other base units have the metric prefix. And then we don't use gram, we use kilogram, which has a metric prefix. There is a reason, and if you're interested in the reason, I knew it at one point, but I forgot. But I know that Veritasium, he's a physicist from Australia that does really good YouTube videos for normal people that want to know physics but don't want to have to go major in it in college. And he did a video on why the kilogram is the base unit of mass and not the gram. There's actually a reason for it. I don't know if it's valid though, I don't remember. Okay, so let me sketch the situation real quick. And I want you guys to understand this. Like there's intuitive understanding here in the equations that we're going to deal with that talk about what's happening at the bottom of the swing versus what's happening at the top. And hopefully you might be able to kind of just tell, right? Where's this guy going to be moving the fastest? It's not moving at the same speed, definitely. Where's he moving the fastest, do you think? At the bottom. Where's he moving the slowest? At the top. If he's not moving fast enough to get through the loop, what happens? It becomes a projectile, right? After no more circular motion, after there's no tension in the spring, it's a projectile. There's no other forces acting but gravity. So it then goes from moving in a circle to a parabola, right? All right. But right now we're focused on the bottom part of the swing. So we're talking about when it's down here. So our first step, now we're analyzing the forces. So now I'm going to draw a free body diagram for the object when it's right here. This is when we can have forces pointing away from the circle, but they're not centrifugal. They're actual forces that are contributing to the centripetal motion. So if you need to stand up and do some jumping jacks, you can if you want. Just do them quietly. Okay. I'm not an officer. You don't salute. And it's down. I'm not supposed to see the palm of your hand when you salute.
Right.
What are we, British?
I don't know.
Why are you bullying?
So what forces are... Okay.
If I allowed to stop.
I saluted you back. You can stop.
Oh, okay.
Okay.
You have to say it.
What forces are acting on the mass at the bottom of the swing safe?
The tension force.
Which points in what direction? Up. Good.
And the centripetal force.
Whoop, whoop.
No.
You never call a force a centripetal force.
Okay.
You say the tension contributes to the centripetal force.
Okay.
If it's gravity on an object in a circular orbit, the gravitational force is the centripetal force, but it doesn't go on the free body diagram.
Okay.
Because any force can be a centripetal force. But there is another force here.
Gravity.
Gravity.
Okay.
Which one's bigger, if any? Or are they the same size? If they're the same size, and this guy's moving, right, in this direction, let's say he's going clockwise, if the net force was 0 because these guys were the same size, what would this guy be doing? He would be moving in a straight line, right? Is that what you're doing, Kevin? Yeah. The net force would be 0. What does Newton's first law tell us about an object if the net force is 0? It moves in a straight line with constant speed, right? So this can't be true. Okay, well, one needs to be bigger. Which one needs to be bigger? The tension. Because the net force has to point where? Towards the center of the circle. The only way for the net force here to point towards the center of the circle is if the tension is larger than mg. Now, is mg for the object going to change as it moves through the motion? No. So what has to change as it moves through the motion to make sure that the net force always points towards the center? The tension. What force needs to change? The tension is the only one that can change. And think about that. When it's in the real quick, say this is the motion. When it's here, the tension points this way, and mg points down. Right? If it's moving up, mg is actually causing it to slow down because it's in the opposite direction that it's moving. So we already know if I'm moving this way and my acceleration's that way, I slow down. Right? So, but then when it gets to over here to this side, now it's like the mirror image. Tension points this way now. mg still points down, still the same size. Now mg is going to make it speed up on the way down, while the tension force kind of keeps it locked into the circle. Right? Does that make sense? Even in AP Physics, we don't analyze this type of motion fully for the whole circle. We only, and this is AP Physics, even AP Physics C, we focus in on the very top, the very bottom, and maybe the sides. For us, we're going to do it at the very bottom today just to illustrate a point. We'll compare it to what would happen at the very top. You guys know if you go through a loop, like a series of loops, at the bottom, you feel a very different sensation than you do when you're at the top. We're going to explain why today. Circular motion explains why. All right, so back to, when we're down here at the bottom of the swing. Free body diagram. What's nice about just analyzing the top and the bottom and the right and the left points is that I don't have any vector decomposition. Any other point, I got vector decomposition, right? And it would be a lot more of a hassle. But here, no vector decomposition. They're either positive or negative in the same direction. So then I got my free body diagram, no vector decomposition. Newton's laws, right? Why am I using Newton's laws when before I didn't need to? Well, now I'm analyzing the forces acting, and so I have to use Newton's second law. And so Newton's second law, net force is equal to mass times acceleration. Well, our net force is going to be centripetal. Over here, the net force isn't centripetal, right? There is a centripetal component to it, but it's not going to be centripetal, which is why this is non-uniform circular motion. It's not constant speed. But here it is. Here, there's no force pointing either in any direction other than towards the circle or away from the circle. So they both are just contributing to the centripetal force at that point in the motion. So the net centripetal force here, remember on the notes it says if it's pointing towards the center, it's positive. So I got a positive tension minus mg. And that's going to, centripetal. That's going to equal, and again, centripetal acceleration, we can substitute v squared over r. And then I'm going to add mg to both sides, and before we even think about plugging numbers in, we're going to look at what this equation is telling us. And use this equation to describe first what the ball is doing and what's happening in the string when I'm swinging that around, and then also what would happen if this was a roller coaster problem. So the tension is then mg plus mv squared over r. So again, the physics is in the equation. Plugging these numbers in and getting your answer, that's arithmetic. This is the important result here. When the string is just sitting there, what's the tension equal to? mg, gravity, the gravitational force, right? That's what it's equal to. So I feel it pulling down on my hand. Newton's third law says if the mass is pulling down on the string is pulling up on the mass, the tension is the same here, and it's pulling down on my hand with the same tension. So this is not uncomfortable, right? It's a little heavy. If I left it here for a while, my arm would get sore or get tired. But then I start doing this. And I'll tell you right now, if I do this fast enough, at the bottom of that swing, this is now causing physical pain. At the top, not so much. At the bottom, it's hurting. You can see it's digging into my hand. The tension got much bigger, right? Especially at the bottom. Does this equation tell us that? Does it illustrate that fact? It absolutely does. When it's just sitting there, tension is equal to mg. When it's moving with some speed v in a vertical circle of radius r, I have to add this number, which is positive, to this number, which gives me more tension. The faster the speed, the bigger this term gets, and the more tension there has to be, right? Which should make sense. The faster I did that, the more uncomfortable my hand got. So does that make sense? Again, this isn't going to be on the test, but I want you to understand it. What if this was Kathleen on her skateboard? You skate, right, Kathleen? You don't? Okay. Kathleen on her skateboard. What's free body diagram? Tension?
Is she just standing on the skateboard?
No, I'm sorry, she's going through the thing.
Okay.
She's going through a loop. This is the bottom of a loop. Crazy. Normal force. I got normal force, And the gravitational force. Perfect. Which one has to be bigger? Normal force. If I was analyzing this situation, what would change over here? There, I've done that problem now. Physics is the same, literally the same. The only difference is the nature of the force that's causing the circular motion. If you're on a skateboard or a roller coaster, it's the normal force. If it's the track, it's the force on the car. If it's the car, if it's the car, it's the normal force from the track on the car. If it's you sitting in the roller coaster, it's the normal forces from the car on you, the car seat on you. Yeah.
Say if you're halfway up the ramp, the normal force is still acting on you, or no?
Depends on how fast you're going. Yeah. If you're going in a full circle, yes, the normal force would be acting that way. Which is why when you go through a loop, remember the normal force is the perception of your weight. Your weight is just mg, it doesn't change. If you were in free fall right now, you would feel weightless, right? That doesn't mean you don't have weight. What are you doing?
Can you answer a conceptual question?
No, dude.
No,
I meant that, okay, no. We're running out of time, come on. Don't just walk back here. What was I saying? Yeah, the normal force, if you're on the side, you actually still feel like you're being pushed down in the seat, right? And that's because you don't feel weightless. So there has to be a force pushing you there. When you go through a loop at the top, you're still stuck in the seat, right? If you're still stuck in the seat, it's not because the seat is pulling you up, it's because it's pushing down on you. And your sensation of that is the Newton's third law, which says, well, you're pushing up on the seat, right? And so your sensation of your weight is the normal force. So when you go through the bottom of a circular arc, your normal force feels larger than your normal force when you're just standing normally, which is why you feel heavier. And then if you start talking about like fighter jets and the banks that they pull, the G's that they pull, this number gets gigantic. It gets many times, like 7, 8, 9 times what this is. And at that point, you got to be super fit or you're going to pass out. Now, one other thing I want to talk about is at the top. What happens at the top? And I got to go through this kind of quick. Again, this isn't on test questions, so you don't have to worry about this, but just understand it because it's cool. At the top, and we're doing Kathleen. She's still doing the loop in her skateboard. So what forces are acting at the top? The gravitational force and the normal force. And the faster she goes, the bigger that normal force is. Okay? The faster you go through a loop, the more you feel like you're being pressed into your seat, even at the top of the loop when you're upside down. So the speed that you go is gonna involve that. If I do the same analysis, I'm going to say the net force is mass times acceleration. The net force now both of them point towards the center of the circle. So I have the normal force plus mg equals, and again, this side always becomes mv squared over r. Now to calculate the normal force, I subtract mg. So this number is always going to be smaller than it is over here, so less force is required to keep you moving in the circle when you're at the top. All right? Hit the like button.